Hello again, physics friends. Today we're going to continue our journey through vector land, and in particular we're going to look at vector arithmetic. What can you do to a vector to change it? How can you combine one vector with another? And in particular we're going to look at how you scale a vector or change its length, and also how you add and subtract one vector from another, and how you multiply vectors together. It turns out there's not a unique way to do that. We're going to talk about two different ways, one called the scalar or dot product, which ends up giving you a scalar. After you start with two vectors, you end up with a scalar. And the other product we'll talk about is the vector or cross product, which is where you start with two vectors and you end up with a third vector. So we'll start with the scalar multiplication. So we have a vector A in blue here, and we're going to multiply it by some number to create a new vector. So let's say we multiply it by 2. If we multiply it by 2, we now are going to have a vector that's twice as long but points in the same direction. We could also make the vector shorter by multiplying by a number less than 1. So here in green is a third vector, which is 1/2 of A. It points in the same direction as A and as 2A, but it is a different vector. So I've used different colors for each. Now, notice that each time I multiply the vector by a scalar number, I so far haven't changed the direction of the vector. It turns out there is a way that you can change the direction of the vector by multiplying by a scalar, but only in a very specific way. See if you can figure that one out. In general, though, we can talk about scaling a vector as taking a scalar, say b, for example, 2 or 1/2 in the case of the red and green, and we can multiply it by a vector, let's say r, for example, a position vector. And we could represent it not only graphically, but we could also choose a coordinate system and show mathematically how we would scale the vector in that coordinate system. So for example, in the Cartesian coordinates, we can write r as x comma y comma z, which is equivalent to saying x in the x hat direction, y in the y hat direction, and z in the z hat direction. And we could scale that vector by a scalar b in the following way. We say b times r is the scaled version of r. That's, at the end of the day, we can write that as b times x, y, and z, which is most simply expressed as bx, by, and bz. So in other words, when you multiply a vector by a scalar, each component of that vector, in this case x, y, and z, gets multiplied by that scalar b. And the result is that your overall vector grows or shrinks in accordance with that scaling factor. Now, there's nothing magical about Cartesian coordinates. We could also express the vector in polar coordinates. We could talk about scaling the vector in polar coordinates. And if you recall, we have a position vector in polar coordinates as a distance from the origin times a direction unit vector. And if we scale that position vector by a scalar b, then that just scales the component. There's only one component in this case, the radial component. And the scaled version of r is just lowercase b times lowercase r, but in the same direction. So we can show this graphically. So if I bring in this here, I have a couple things going on. I have my unit vector r hat in blue, and I have my purple vector, which is the position vector r. And what about this r? Well, that is the magnitude of the purple vector, okay? That's the distance from the origin. So when I scale by the scalar b, I can think of that as just changing the length, but not the direction of the vector, br. So in this case, b is a number that's bigger than 0 and less than 1. Now, I've said that the scaling doesn't change the direction, but there actually is a way to change the direction. And think about the sign of b. So far, all of the examples we've done, in all of the examples we've done, this scaling factor, in this case b, has been a positive number. What happens when b gets negative? So think about that for a minute. Our next topic is going to be vector addition and subtraction, and then we'll get to vector products after that. So now that we have scaling of vectors under our belts, we can turn to vector addition and subtraction, and we'll see that vector subtraction is really just addition plus scaling, scaling by -1. So let's consider the following. We have some vector A in blue and some vector B in red, and we want to know the quantity A plus B. So we haven't specified anything about a coordinate system, and it turns out we don't need to, right? Because vectors exist independent of the coordinate systems. So all we need to do is recognize that we can add A to B by connecting A and B tip to tail. So let me make a copy of A here, and I'll make a copy of B here, and I can then move B around so that it sits tip to tail with A, and the resultant vector, of course, is just A plus B, starting at A and ending at the end of B. Start at the start of A, end at the end of B. So in other words, if you start here at the beginning of A, you march along A, and then you continue along B, and you end up at this point. Well, you could have also gotten there just by going along the purple path. So A plus B is represented by this purple vector. Well, then how about vector subtraction, A minus B? Well, we can recognize that A minus B is A plus negative B, or A plus -1 times B. So we know how to scale by a scalar, in this case -1, and we know how to do addition. So all we have to do first is find minus B. Well, minus B is the same vector as B, but pointed in the opposite direction. So if you remember back to the question of can you change the direction of a vector by scalar multiplication, well, here's how you do it. You multiply by -1. So A plus minus B will look like the following. I'll take my minus B vector and I add it to the vector A tip to tail, and my resulting vector in that case will be A minus B. Or A plus negative B. So this is how you do it graphically, and we never specified a coordinate system, nor do you have to. These vectors are entities independent of coordinates. But it's often convenient to use a coordinate system to calculate mathematically the components of the resulting vectors. So let's see how to do that next. So if we have two vectors, A and B, in Cartesian coordinates, we can write the components as A sub x, A sub y, and A sub z, and similarly for B. And then we can ask the question, what is the vector sum A plus B? And for that, we can say, okay, well, this is just the sum of each component individually. AX plus BX is the x component of the resulting vector, and then AY plus BY and AZ plus BZ for the second and third components. So very straightforward, and this, of course, arises because our shorthand bracket notation is really hiding these unit vectors, AX in the x hat direction, AY in the y hat direction, and AZ in the z hat direction. Same for B. And so when you add these together, you're just combining term by term the x components, and that goes into the x component of the resulting vector. The y components are added together, and so on and so forth. And notice that subtraction would be handled in exactly the same way. If we had A minus B instead of A plus B, then each of our plus signs here would turn to a minus sign. So we could say A plus or minus B is AX plus or minus BX, same for Y and same for Z. What about in polar coordinates? Let's take a look at that. Well, first of all, how do we write down these vectors A and B in 2D polar coordinates? Well, what we already know from our previous work is that the vector A has a magnitude of A in the r hat direction, and the vector B has a magnitude of B also in the r hat direction. And you may be tempted to say A plus B is simply sum up the components A and B in magnitude and point those in the r hat direction. But this is most certainly wrong, and you can see why that must be true, because what if I chose two other vectors, let's call them C and D, and I have C pointing one way and I have D pointing exactly the opposite way, Same magnitude, opposite direction. Okay, so these vectors are the same length. Well, in that case, I know that c plus d is going to give me 0 because c is equal to minus d. So when I add them together, I get 0. But the magnitude of c plus the magnitude of d are not 0. Okay, so it's not okay in polar coordinates just to add the r hat component. But that's weird because the r hat component is the only component. So what's going on here? Well, we can see the issue if we draw this out. And the issue now is that the r hat vectors that we had just labeled r hat before, these guys, they're not the same vector. The vector A points in one direction and has a unit vector pointing in that direction, but the B vector is pointing in general in some other direction, so its unit vector is different. So when we write here r hat and r hat for the two vectors A and B, those are different r hat vectors, so we really should call these r A hat and r B hat, and just acknowledge that these two vectors are not in general the same. We're going to come back to this when we talk about time derivatives of unit vectors. In Cartesian coordinates, the x hat vector always points to the right, and y hat always up, and z hat always out of the page. They never change. They don't evolve in time or in position. The r hat and phi hat vectors for 2D polar coordinates, though, in general do evolve. And so we have to keep track of them. So we're going to start, in the future, we're going to take derivatives, learn how to take derivatives of unit vectors for unit vectors that are changing. So here we can just summarize this by saying Cartesian unit vectors are constant, 2D polar unit vectors are not constant. Okay, so far we've talked about scaling a vector, and we've used that in addition to addition to figure out how to subtract vectors. And next we're going to move on to multiplying vectors, specifically how to take two different kinds of products, the so-called scalar or dot product and the vector or cross product. For vector products, there's two main ones that we're going to make use of in this class. One is the scalar or dot product, the other is the vector or cross product. With a scalar or dot product, the input is two vectors and the output is a scalar, hence the term scalar product. Let's take as a starting point two vectors, r and s here, and the notation we'll use for the dot product is r dot s. And we can say that r dot s is given by the magnitude of r times the magnitude of s times the cosine of the angle in between r and s, like so. Okay? And this approach to defining the dot product or scalar product does not refer to coordinates in any way or components in any way. All we need to know is the length of one vector, the length of the other vector, and the angle in between them. These are coordinate independent quantities. It is equivalent, though, to say that r dot s is equal to the x component of r times the x component of s added to the similar pairings for the y and the z coordinates. And that arises because if you think of r as having an x, y, and z component, same for s, then when you take the dot product of r and s, you can imagine dotting this component, rx in the x hat direction, into each of the three components for s. But x hat dotted with x hat is going to be 1 because the length of each is 1 and the angle between them 0, so cosine of 0 is 1. But x hat dotted into y hat is going to be 0 because they're perpendicular to each other, and cosine of 90 degrees is 0. So any pairing of a unit vector with a different unit vector will give you 0, and the only quantities that survive in the dot product are x hat dotted itself, y hat dotted itself, z hat dotted itself, and so we get this rx sx plus same for y and z. Okay, so both of these ways of expressing the dot product are equivalent to each other, and we might make use of both throughout the term. So there's many uses of the dot product. One useful one is to pick out a component of a given vector in a particular direction. Okay, so for example, let's say I have this vector s, and I want to know what is the component of s in the y direction? Well, if I take the dot product of s with y, then what I'm left with is simply sy. So I have sx times 0 coming from the first components, and similarly for sy times the y component of the unit vector, sz times the z component of the unit vector, but everything is 0 in that right-hand side except for the second term. So s dot y will give me the length of my vector s in the y direction. And notice that we could also have expressed this as mag s times magnitude of the y hat vector times the cosine of the angle in between them. Why is that the y component of the vector s? Well, let's take a look. So if I draw my s vector here in a coordinate system, and I draw my y unit vector, and I'm taking the dot product of s with the y unit vector, I get mag s times mag y times the cosine of the angle between them. The magnitude of y is simply 1, because it's a unit vector, has unit length. And so what we see then is magnitude of s times the cosine of theta. So if we look at a triangle whose hypotenuse is the red line s, it has a length of magnitude s. Well, the y component is the left-hand side of that triangle. I can write that as the hypotenuse times the cosine of this angle theta. Right? Cosine is adjacent over hypotenuse. And that's exactly what I got by taking the dot product. So I can pick out a component of a vector in a particular direction. It does not have to be a Cartesian direction, x, y, and z. It can be any arbitrary direction. So that's definitely one useful function of the dot product. Another really useful purpose of the dot product is to find the magnitude or length of a vector. So imagine we take some vector r and we dot it with itself. When we do that, we see from before that we need to know the magnitude of the vector in both cases and the angle between it. But the angle between a vector and itself is 0, and cosine of 0 is 1. So when you dot a vector with itself, you get back the square of the magnitude of that vector. Okay? And we know that the dot product can also be written in Cartesian coordinates as the sum of the products of the components of each vector. But here it's the vector dotted with itself. So we have rx squared plus ry squared plus rz squared. So this is just like the Pythagorean theorem. And then we can solve for the magnitude by square rooting both sides, right? So we get the Pythagorean theorem generalized into 3 dimensions like this. So where might this show up? Well, one place it shows up is when you think about the kinetic energy. Kinetic energy depends on the square of the speed of an object. The velocity doesn't really matter because the kinetic energy doesn't depend on the direction the object is going. It just depends on the speed of that object, in this case squared. So we can write that in terms of our knowledge of the vector velocity by saying instead of v squared, we can write that as v vector dotted with itself. And we can make use of the previous result to say that v squared for a given velocity is simply the sum of the squares of the components of that velocity. The final vector product that I'd like to focus on today is the so-called cross product, in which you have 2 vectors as inputs and you get a vector out as your output. Okay, so we'll finally here wrap up with a discussion of the cross product, in which you input 2 vectors and you output another vector, but this resulting vector has a special property. It's perpendicular to the first 2, and it has a magnitude equal to the area of the parallelogram defined by the first 2 vectors. What do I mean by that? So here I've drawn 2 vectors, s and r again, and they define a parallelogram, and the area of that parallelogram is equivalent to the magnitude of s cross r. In other words, if I have s cross r, I have a magnitude for that quantity, which is equal to this area. And it has a direction which is perpendicular to s and r and given by the right-hand rule. So the right-hand rule says point your fingers along the direction of s, curl them towards r, and your thumb points in the direction of the cross product. In this case, that would be into the page. How actually do we write the area of the parallelogram? Well, the area of a parallelogram is equal to the base times the height. So here the base would be the magnitude of the blue vector r, and the height would be the length of s times the sine of this angle theta. Okay, so we could write this as mag s, mag r, times the sine of the angle theta. And we can see that when that angle goes to 0, you smush s and r, they're parallel to each other. That means the parallelogram will have 0 area, and indeed sine of theta of 0 is 0. Okay. So if two vectors are parallel, their cross product is 0, and the cross product is maximized when the two vectors are perpendicular. It's kind of the opposite of the dot product. Dot product is maximized when the two vectors are parallel, and the dot product is 0 when the two vectors are perpendicular. Well, how would we write out, using Cartesian components, the resulting cross product? Well, why don't we say we want to compute the cross product of s and r in that order, s cross r, and we'll call the result u. Well, it turns out that this vector u is given by, we can write it as the determinant of a 3 by 3 matrix, where the first row of that matrix are the unit vectors, x, y, and z. The second row is the first vector in the cross product, s, so we write down the 3 components. And the last row is the components of the second vector in the product. Okay, and that determinant we can write in the following way: x hat, y hat, and z hat. So there's lots of ways to write this out, but one way is to think of the determinant being constructed in the following way. Take the matrix that we started with, and then I copy the first 2 columns over here in purple, and then I construct these 3 lines, and that tells me what to do. I'm going to take these 3 quantities and multiply them all together and write them down. So I'll have s, y, r, z times x hat. And I do the same for the next 2 red lines. And then I repeat the process going in the other direction, and those all take a minus sign. So we can see here the blue line that contains the x hat unit vector is going to involve sz and ry, and so on and so forth for the y hat and z hat components, and every single one of those terms gets a minus sign. And so at the end of the day, the vector s cross r, it's a vector, is the following on the right-hand side. It consists of pairs of different components from the original vectors. And notice that the x component of the resulting vector involves the y and the z components of the input vectors. The y component involves the x and z components, and the z component involves x and y components of the input vectors. So where does the cross product show up in the context of this course in mechanics? Well, it primarily features in angular momentum. So that's where we're going to come up against this in the future, and that'll take some time for us to get there, but when we get there, you'll see terms that look like this. The angular momentum, L, is equal to the position vector of an object crossed into its linear momentum vector, and the associated torque in a problem, which we'll use capital gamma for, is given by the cross product of 2 vectors, the position vector and any force that's present in the system. So we're going to come back to cross product later in the course when we get into rotational motion and angular momentum. So that's it for now for our overview of how you can do vector arithmetic. We talked about scaling a vector, doing addition and subtraction, dot product and cross product. In another video, we'll explore how you do derivatives, time derivatives in particular, for a unit vector. But for now, take care and be well, and we'll see you next time.